Welcome everybody to the eighth talk of the Virtual Exchange Seminars in Quantum Mobile Networks. Before starting today, I would like to ask the audience, as usual, if there is any question regarding the previous presentation. For the students who need the CTS, as usual, you find in the chat a link to the exercises related to this talk and a link to the evaluation sheets where you can express your opinion on today's talk. So if there is no question from the students, we can introduce today's presentation. So the topic today is effects of mobility patterns on QMN performance. It will be given by Minrui from the Nanyang Technological University of Singapore and Jakob Schärer from the University of Bern, Switzerland. The duration will be, as usual, around 30 minutes, will be followed by 10-15 minute question and answer session. As usual, the questions you can either write them in the chat and then I will pick them at the end of the talk, or you can directly ask the presenters at the end of their presentation. So now the first presenter may share the screen and start their presentation.
So today we are going to share the effect of mobility items in of quantum mobile networks performance. We have two presenters on this topic. Minrui from Nanyang Technology University, Singapore, and the another presenter is Jakob Schärer from University of Bern, Switzerland. First, let us revise what is the quantum network. The quantum network, in fact, if we want the quantum network, we can regard the quantum network as a point-to-point protocol of the quantum key distribution. On one hand, the point-to-P2P protocol is unstable to simultaneously achieve high rates and long distance. On the other hand, it's not yet fully understood in protocols with quantum repeaters. As shown in Figure 1, between the source node and the destination node, there can be multiple repeaters, so that we need to estimate the channel capacity with the quantum repeaters. First of all, we want to introduce a concept of the pyramidal, the PLOB bound. This bound indicates as long as entanglement bit or secret bits over a noisy channel. Under the channel's transmissivity eta, the maximum weight is equal to minor log 2 1 minus eta. This can be achieved by in that paper, the author would like to achieve the most general and adaptive protocol by using one single letter upper bound, as we read before, the eta, from a single repeater chain to an arbitrary complex quantum channel. No matter it is a single repeater chain or a complex quantum network, it can be represented by this upper bound with only one single letter. And then the routing scheme in the quantum network should be follow the single path one, and it can also be extended to the multi-path one. So let us revise the ultimate limits of the repeater chain. As we can observe from Figure 1, if Alice would like to communicate with Bob, it can directly transmit the signal to Bob, but the signal of Alice can also be amplified and be forward and amplified by multiple repeater. It cannot be amplified. be followed by multiple repeaters, so that as the number of the repeater increase, we can observe from the figure 2, as the number of the repeater increase, the channel capacity increase as well. That's because the total loss in land decrease a lot as the number of repeater increase. Considering an optical fiber with transmitted phi, and then we insert unrepeaters so that the fiber is split into n+1 noisy channels. Therefore, maybe we already learned the concept that when the propagation distance increase, the noise become larger, so that the fidelity of the quantum channel of the entangled pair become lower. So that if we split the whole fiber into n+1 noisy channel, so that the fidelity of each segment can be increased, so that the optimal configuration corresponding to the equidistant repeater, so that the eta minute equals to eta square n+1. Therefore, we can give the maximum capacity of this noisy channel as shown in this equation. Moreover, the channel capacity of the distillable chain and network can be listed in this table. First of all, let us review the noisy channel one. The noisy channel one indicates that when the transmissive is eta, so the capacity under repeater I under a chain repeater is minor log2 1 minor the minimum eta. And then we can also have the single path one and the multi-path capacity. In addition, we can also give the Q limit amplifier, which is minor log2 1 minor, and that this table can be found in the paper. I will share with you later. So this is also shared by the organizer. And then after we have formulated the channel capacity of the point-to-point quantum network, quantum channel, and then we would like to consider the channel capacity of the hybrid quantum network. The hybrid quantum network indicates that the network with hybrid structure, including the optical fiber channel and the field space channel. And then the interplay between the channel quality within the network substructure must be carefully considered. First of all, we have the globally distant fiber subnetwork, and then the fiber subnetwork is connected to a satellite backbone network. So in this hybrid structure, we need to consider the resource requirement, not only in the ground interconnect fiber network, but also the satellite-based quantum internet, as well as the wireless field-space subnetworks. So in this type of network, we will have the network routing scheme. The first one is the single path routing, and the second one is the multi-path routing. And we can also have the quantum network over fading channel, includes slow fading and fast fading. Slow fading indicates that the distance is large, and then the channel capacity change slightly. The channel capacity is stable, but the fast fading is that the distance is low, and then the channel capacity is dynamic. Finally, we still have the characteristic of the fading channel that the capacity can be represented by this mathematical equation, and then it can also be, the channel capacity can also be described within a probability density function f, where the tau indicates the transmissivity and the n represents the thermal noise, which are probabilistic. In addition to the optical fiber quantum networks, the field-space quantum communication have several differences. The first one is the transmissivity is different from the fiber one, and then the atmosphere can also affect the fading performance of the field-space quantum links. Finally, the weak turbulence, thermal noise, that's because the temperature is different under different weather conditions, so that it can also affect the performance of field-space quantum communication. Finally, the noise superposition and frequency filter, the design scheme can also affect the performance of the field-space quantum communication. So there are three important field-space channels: the ground-based channel, the ground satellite channels, the inter-satellite channel. And in this figure, we can show the performance of these three types of channels under the increasing distance. As we can observe, usually the ground-based channel is high. The transmissivity of the ground-based channel is high, and then for the ground satellite channel, the transmissibility is a little bit lower. And that's all for the quantum channel 1. And then let's invite the Jakobi to introduce the mobility pattern that will affect the performance of the network capacity.
So now that Minrui has showed us how the actually the static performance is of quantum links, I would like to discuss with you a bit about mobility. And actually, there is not a lot of research done yet about the performance impact of the different mobility models we know. So what we like to do is we like to discuss a bit what we know about existing mobile networks and try to extrapolate to and discuss and probably speculate a bit what that would mean for mobile quantum networks. So why do we need this? Mainly, a lot of the proposed quantum networks actually have mobile nodes in it. So we talk about satellites, we talk about drones, and these are typically then combined somehow with ground stations. So we have somehow a mixed mobility pattern. We have very different patterns here we can observe in them. And what does this mobility actually mean for a network? Mainly, the mobility of the nodes means that the topology of the network changes all the time during the operation. And these topology changes actually depend on how the nodes move through space. And there are very different patterns, like we'll discuss later. And the topology changes then typically yield for new routes. So we have to rebuild routes in the network. And this generates rerouting overhead and might also affect the performance of the network. So what mobility patterns do we actually know, and what is a mobility pattern? A mobility pattern is what we observe in the reality. So the pattern is we have some random mobility. These are random movements of nodes in various directions. So we just have some nodes moving around. Or we have directed mobility. This is mobility along streets, but could be also a trajectory of a satellite. And then we also know group mobilities. This could probably be cars driving on the same street. But we also have some stationarity, or at least I said that before in this image with the satellites and the drones. But the stationarity in a broader aspect is probably just a group mobility where the complete Earth is one group that is moving through space. If we have satellites, and probably satellites that are not in the same orbit or not in the Earth's orbit. The patterns are actually the ground truth. And what we try to do is we try to build mobility models that is able to somehow describe these patterns pretty accurately, so that we can use these models to then simulate or perform simulations where we can evaluate our algorithms and use that to actually see how good the algorithms are. And the literature knows quite a lot of different mobility models from the mobile networks, because there has been quite a lot of research in the past 2 or 3 decades. And one very important mobility model or group of mobility models are the entity mobility models. These are models where we actually move individual nodes around. So this here we know, for example, the random walk mobility model. This is just each node is randomly driving through space. We have a random waypoint mobility model. Here we actually randomly create waypoints where we then let the nodes move along these waypoints. Or the random direction mobility model. This is a model where the nodes are driving in one direction until they end at the end of the map and then bounce off, like you know it, for example, in the game Pong. So it's just the nodes are moving within the borders of the map. And so on. The city section mobility model is probably interesting for one-nets, where the cars are moving along streets. Here, very famous is, for example, the, Manhattan model, where we have this chessboard-like map where the cars are driving through a grid. Then we have the group mobility models. These are the patterns where groups are moving around. Here is, for example, the pursue mobility model. Here we have one node that is actually leading a group of other nodes, and the other nodes are just following this node and regrouping 1 and 10. And in the end, we can also have a group, many groups that are moving around, and this then reproduces our mobility patterns. But then we also find some more exotic mobility models in the literature that are used to actually evaluate mobile networks. Here was one example in the literature where they just randomly distribute the nodes over a grid, and they do that for every time slot. So actually the nodes are not following a certain path, they are just placed randomly somewhere, and depending on that, they generate new peer lists, which are then used for the routing. So I have now shown you some examples of mobility models. There are actually also more, because this was a wide research field for quite long. But now the question is, does this really matter? Does it change the routing? Does it change the performance of mobile networks if we have these different models, or could we just always use the random walk model where we just have the nodes moving in random directions with random speeds? And the answer is yes, it's actually has quite a huge impact. I have here this paper, a survey of mobile models for ad hoc networks. It's actually quite old, but very well cited paper from Cam Tracy. And they did in 2002, I guess, a very good survey and compared the different or some of these models to actually see what is the effect of the different models. And what we see here, for example, the contract control packet overhead, here we can observe that when we have entity mobility models with a lot of direction changes, then we have also a high overhead because we have to reroute all the time. On the other hand, if we have group mobility models where the nodes are more or less driving in the same direction, then they don't have to reroute that much, and so we have less control packet overhead. If we look at the packet delivery ratio, so how much packet loss we have, we can also see a clear difference. Here we have a better performance for modality models with little topology change. Somehow obvious we have less link failures, but we have also a better performance for nodes with a high randomness. So for random walk is actually pretty good, but this is mainly because it has less link failures, I guess, because it's changing the routes pretty quickly, and the nodes are pretty good distributed over the complete map, while for group models, probably the network becomes split if there are patterns and so on. So these are actually, but this is not so clear in the paper, but if we look at these graphs here, we have some tendency. What we can also see is that the speed has actually quite huge impact on the performance for this metric as well. What we have done as well, probably because the paper is pretty old, we shouldn't look too much on the average delay. I guess today these delays are better, but the tendency of the impact of the mobility patterns is still meaningful, I guess. So if we look at the average hop count, which might be interesting for the quantum mobile networks, as we have heard before from Minrui, then we can see that actually the mobility models again have quite a huge impact on this metric. And then also on the average end-to-end delay, but this is somehow correlated to the hop count. If we have more hops, then we actually also need more time to forward a packet through the network. What is the time? I guess I skipped this one. So what we can say is for the classical mobility patterns, the different patterns have, for the classical mobility networks, the different patterns have quite a huge impact on the performance on the network itself. Well, let's say of the mobility models, for the patterns, I don't think that we should look at real world experiments and not on the models to be absolutely sure, but I think the tendency is very clear. So with all these mobility models, in the end, we typically have just one model to somehow represent the complete system or environment where we, for example, also could have different objects, different types of nodes. Like in a VANET, we could have a car that is moving around, but we could also, we often have roadside units that are not moving around. So in the end, the types of networks would typically be somehow a combination of different mobility models. But if you look in the research, they are mostly just using one mobility model for the evaluation. And what we see here is we have the ad hoc, mobile ad hoc networks, which are rather slow mobility with high randomness. So we would here use a slow random mobility model to actually evaluate such a network. For the vehicular ad hoc networks, we have a high mobility with constraints of degrees of freedom. So the cars are driving on the street, and we sometimes have roadside units which are fixed somewhere on the border of the street. You would use probably a group mobility model or a city section mobility model. Then we have also the VANETs, where we have drones or UAVs flying around. They have a high mobility, a high degree of freedom. So we would need, or we would model that with a fast random mobility model, could be random walk. Exactly, and then you have satellite networks where you have predictable trajectories. I don't know if we would actually use a mobility model, or this would be also a model as well, but we could actually just calculate it on the true trajectories, because the satellites are pretty predictable where they precisely are. So what would be the mobility of a quantum mobile network? So there's not a lot of research yet around, but if we speculate a bit, so we have the satellites, this is a predictable trajectory, probably can just calculate it, probably we would use a direction model, which is just sending it in one direction. But then we have also the UAVs, which have a very high, can have high speeds, fast direction changes. So we have a very high mobility with high degree of freedoms. And then we have the ground stations with the stationary nodes, which only move in this group pattern if we have more of them with the world completely. So in the end, we like for also one-nets or all these types of networks, also here we would require a rather mixed mobility pattern than just choosing one, I guess. And so this would be one research question or one thing that we can see in the literature. It's actually not really described how to model this. So this would be an interesting task to actually find a new model or way how to model that. But so if we then had found a mobility model for quantum mobile networks, what is actually, or what could be interesting to actually look at and to evaluate? So what we have seen is the mobility or the models actually really have an effect on how many control packets we have, so how often do we need to reroute and so forth. And in the quantum networks we have seen in this seminar, we often have a hybrid architecture where we use classical networks combined with the quantum links, and we use the classical links actually to set up the quantum links and so on. And I guess setting up a quantum link is much more expensive than a classical link. So it would be interesting to use such mobility models to actually evaluate how expensive would that be to set up this link, and how much overhead do we have if we have this mobility. And then also, but this wouldn't change to the classical network much, because it's more or less the same as we know it from the current mobile networks. The classical link for sure is also these limits we have from this network, we will also take to this hybrid quantum networks, because we somehow need to control the quantum links. So we will still be bound to those. If we extrapolate it a bit and allow us to do a bit of speculation, then we would say that we also would have an increased packet loss rate at higher speeds, like in the classical networks, at least for the classical links. But also, I guess we would have increased link failures for the quantum challenge, because if the nodes are moving out of range, then the link fails and we have to reroute that. I guess we would have a mobility pattern with high randomness in terms of the UAVs that could be used for quantum links. And so we would have here a high control overhead as well, which would be expensive, or should be evaluated how much more expensive is that than a standard or a static quantum link. And what we also will have, what we have seen in the mobile or in the classical mobile networks, we have a higher hop count when we have a higher mobility in the network. So this would also account for the quantum networks, I guess. And here we would require more repeaters. And like we have seen in the first part of Minrui, this would also affect actually the same characteristics, as he has seen that if we increase the repeaters, then we have actually a better or higher capacity. So to conclude, the different mobility patterns might have an impact on the performance of QMN. As far as I have interpreted, I'm quite sure that it will be that way. I think also a conclusion, there should be more research about what will be the real mobility models of quantum networks, so that we can actually do these evaluations and build the routers and repeaters that they can handle that. And Exactly. And I'm not so sure about the last part now, if I have understood the previous presentation correct. But we can take that to the discussion because here are a lot of open questions in this field, I guess. This is questions for the students, some references, and so I would like to induce a discussion. Thank you very much.
Thank you, Jakob and Minrui, for your presentation. So we can open the question and answer session. So is there anybody from the audience who has questions for the students?
So first of all, thank you for your presentation. I have a question to Minrui mainly because it was for the first part. And so you showed some capacity measures. Did you find anything about RF links? Because we heard in some previous presentations that you can also have quantum communication over classical RF links in kind of a way like that.
No, I didn't found the papers that the capacity evaluation for the RF links. Maybe they haven't done this type of job.
Okay, thank you.
Yeah.
Diego.
Hi, so great presentation, everyone. I think it was really nice, very interesting. For the first presentation, can you go to the table where you have different capacities there? I kind of didn't understand very well some things there. I think it's the Pirandola paper. Yeah, this one. Yeah. So yeah, so as the first question, this is only from like considering fiber links, right? Not RF, and I think that's okay. So can you explain? I mean, these are different types of networks. So it has like chain networks, single path with multipath, and the capacity of the channel and the system will change from the different way that we arrange the network, right? So can you explain? I mean, I'm not so much from the area. So transmittivity is what? Is the capacity to transmit a data? Is that? So like transmissivity, yeah.
Yes, I think the capacity is estimated based on the number of bits per use. So the number of bits can also be regarded as the amount of data.
Okay, so it's just the kind of the amount of data that you can transmit there. So can you just go back to the table and so this what is N there? So it's the number of link of nodes.
You mean the eta here?
Yes.
Oh, the eta is the transmissivity of each segment of the transit quantum channel, transit quantum link, such as for this quantum link, so there are n plus one channel sublink. Yeah, so the n is
so this means that okay, so means that which one of this is like better? So if you go to the table, have different capacities, right? Which one is have the best capacity? Is the chain one or the multipath? What?
There must be a trade-off. There is no the best one, but under different environment, under different segmentation or routing scheme, there must be a trade-off to evaluate to be balanced. So for example, for the noisy channel, so for the chain one is rather simple, but for the network one, So the network one is represented by the Ln. So it is different. The estimation of the capacity is different, but it is determined by but they are determined by the routing scheme and the channel capacity of each segment, so that there should be a trade-off. There is no best solution, but I think under different environment, we can find the most suitable one.
Okay. Thanks very much for the question.
Okay. Do we have any more questions from the audience?
Yeah.
Yeah, Andre.
I will have some kind of related questions. So about these capacities. So how is it defined here? Is it the classical capacity of the channel, or because if we have a quantum channel, then the capacity will be something else. So I mean, it would be the fidelity of the transmitted quantum state or something like.
Yes. It is different from the classical channel. That's because it is for the quantum channel. But the estimation is from the classic channel. That's because we need to have the classic data to be transmitted, and then we can estimate the number of available data.
Okay, so but this capacity here, it's a classical capacity, so that's why it's in bit.
I think they are equals. The quantum capacity, the quantum capacity. How can I say? They are equal with each other. No. Let me put it in this way. So we first have the quantum channel capacity, and then we can have the classical channel capacity under the quantum channel, and then we use the classic one to represent the quantum one.
Okay. And maybe another related question for both of you. So you mentioned so let's say if we look at the quantum mobile network, so depending on the different type of mobility. So now I guess I don't know the answer, and I don't know if there is one. So one needs to compare the effect on the network. You need some kind of figure of merits of the network. So that could be the capacity in that case. But I have the feeling that in the quantum network, then it could be quite different. So I mean, it depends for what do you want to use the quantum network. So if you want to distribute entanglements, that may be a different task that generate a secret key in QKD. So
I see. Yes. Most of this channel. Yes. Most of this channel estimation is for the QKD. They are estimating the capacity of the QKD network. So,
okay.
So that's why.
But then if you would think of the quantum network to have distributed quantum computation, for instance, that may be another quantity that you will be interested in,
Yeah, I think it is interesting. Yeah, that should be interesting. Sure. It is good. This question is good. Inspiring.
Do we have more questions? Maybe, okay, then I can ask one. So to Minrui, again to this formula. So apparently everybody likes this chain of repeaters a lot. So there is something that it seems a little bit counterintuitive, especially if you see in the previous plot where you have the different curves that you see, the more repeaters you have, the higher is the capacity. So here you would imagine if you have a bottleneck, then you would bring down the capacity. So can you give like an intuitive explanation why in a linear chain, the more repeaters leads to a higher capacity? Because one naive person from the classical networks would imagine at best it stays constant, the end-to-end capacity. But here we see that actually it goes up. So why?
I think first of all, we all know that in a quantum network, the entangled qubit cannot be amplified. It can only be forward, so it cannot be amplified. is the first point. Then we all know that in our previous seminar, we have also, I think we already discussed it, as the distance of the quantum link increase, and then the fidelity of the entangled pair decrease. It follows the log, it follows the exponential law. And then as the number of the quantum repeater increase, so the distance between each quantum repeater decrease, so that the fidelity in each segment increase. However, the deployment cost of the quantum repeater is high, so there should be a balance between the number of quantum repeaters and the fidelity in that quantum channel.
Okay. Okay, yes, very clear. So here the trick to read this graph is that the actual physical distance between A and B remains the same. You just fraction the distance in more hops so that the fidelity increase exponentially. Okay. And then
Yes.
one to Jakob. You skipped one slide. It actually was interesting. Can you maybe spend 1 minute on that? Because it's I think it's worth it.
Actually, what we have here is from this paper where they just randomly dropped the nodes over the network, and what they researched here is actually how well is the capacity for the different densities in the squares, what you see in this, how they drop the nodes on the space, and what we can see here, if we have a density of almost 2, then we have actually the best capacity, and it's then declining if we have more users. And this is due to when we add more users, then we add redundancy with their protocol, and therefore we actually have a high reliability. So it's better for forwarding the packets. But what we also have is that we have not so much space because we use it for the redundant information. What we have then also is the average delay that they evaluate, but this is more or less the same what we have seen in the previous slides. Just here for their how they distribute it. They also evaluate it. Well, actually, now in the graphs they don't do that, but they in the paper they also discuss how well they distribute the nodes over the network. So we have this IID, independent distribution of the nodes, where they're just randomly or that they are somehow more cluttered, what can also have an impact on it. But it's mainly the density which is important here for the capacity.
So if I understand correctly, this plot on the top shows that if you have very sparse density, then you don't have capacity because maybe there is no link to be established.
There is no connection, yes.
And if you have too many, maybe you have effects like interference and other things.
Yes, but in the end, it's for forwarding the information, it's the best because we have more redundancy with their protocol. So they forward information twice, and so it's not so easily lost. But the capacity is therefore declining.
Okay, I think Diego has a question, another one.
Yeah, maybe in the way that the last question, in terms of you show different like mobility models. You have entity models and also the group mobility models. Which one do you think that would be like more not easy but more feasible to be adapted to quantum mobile networks, or maybe both, or different situations there?
Well, in the end, with these models, we try to somehow simulate the reality as close as possible. And I think what they in a lot of papers do is that they just use one approach to actually simulate the mobility of the nodes, and then they use it for all the nodes. It's a bit different in the VANETs, where they often use the roadside units, and then also will use that in the evaluation. But you very often just have papers where they use the random path model. But I think to have in the quantum networks, to have a really good simulation, we should actually use 3 different models, so that we have one where we just have, or depending on the network we are actually trying to simulate. But if we have the assumption of the network with satellites, with UAVs and ground stations, then I actually would use 3 different models to actually really model the movement of the different types of network nodes, and then actually use that also for simulation. It's not so easy to implement like the model where they just randomly distributed for each round on the paper, but I think if we want to know how expensive it is to build quantum links on the changing network topologies, this would really increase the accuracy of our simulation models.
So the idea is that from different behavior of the mobile networks, you have to kind of have different links, like entanglement generation rates, or maybe have to have more memory inside of the links, or this kind of stuff will change. This is something that can be evaluated there, or
yes. Exactly, because this one good example, the memory of the repeaters. If we have high mobility and we need to build a lot of new links to other nodes, then we also need a much bigger cache of entangled qubits. If we have seen that before in the routing presentation, they have shown us a very interesting slide where they showed how we have this cache for the qubits. And if we have a lot of node change, then either we just drop all the entangled states we have, or we somehow can cache them. So we need bigger caches or memories to store them. And this, I think the mobility will have a huge impact on the design of the repeaters and the nodes, just because if you have to change the links every 2 connections or every 2 packets you have sent, then you need much more capacity to store information.
Thank you. That's very, very interesting. Thank you.
Okay, so let's see if there is any further, maybe if there is a final question. Okay, so if not, I guess we can thank the speakers for their talk. So thank you so much for participating today. And since today is the last talk of the series, I would also like to thank all the other students and the advisors who participated in this initiative. I'm really happy that we managed to gain such a huge audience, and from such a large number of countries all over the world. So this is really truly an exceptional results that we had. If you need an evaluation for me, a grade, just contact me with your supervisor in copy. Okay, so then again, thanks everybody for joining today, and I see you soon. Yeah. Yes.
Thanks.
You.
Cheers.
Bye. Bye.
Bye.
Bye.
Thank you. Bye.
Bye.
Thank you. Bye.